We're going to be talking about 3D graphics SDKs today, OpenGL, Metal, and SceneKit. And so I hope that's what you're in the mood for. First off, how many people have done some 3D programming so far? Oh, everyone. Wow. Okay. How many people have used OpenGL? A lot. Oh, okay. Good. We'll go fast through that part. Well, what about OpenGL with shaders? Okay, most people. What about SceneKit? How many people have used SceneKit? A smattering. And what about Metal? How many people have gotten Metal so far? Just Jeff. Okay. Good. Okay, that's helpful to know. So as you all know, these are the three SDKs that we have on iOS and now actually macOS for doing 3D graphics. And so what I wanted to talk about today is what are the differences between the two? What do each of them look like in terms of code? How do you tackle problem solving in each of the different SDKs, and really what differentiates them from each other? And we'll talk a bit about MetalKit and Model.io as well, which are two of the new things they introduced this summer to help out with these things. So please feel free to ask questions during the presentation. I'm happy to do that. So we're going to start, well, first we'll start with a little overview that if you have these three SDKs, they actually stack up very nicely in a ladder of abstraction where you have SceneKit at the top and kind of OpenGL in the middle and Metal down at the bottom. And your complexity of writing rendering algorithm, or not actually a rendering algorithm, but just a piece of graphics code, increases as you go towards Metal, and it decreases as you go up to SceneKit. But likewise, the power increases as you get down to Metal and decreases as you go up to SceneKit, although there's sometimes trade-offs in there. But when we use each of these SDKs, we think about different things. So with SceneKit, we get to think about objects and transforms and effects, particle systems, things like that. With OpenGL, we have to go down to the mesh level. We think about how our mesh is arranged. We think about shaders. We think about the OpenGL state machine. With Metal, we actually get even lower. We have all the same things in OpenGL that we have to think about. We have the Metal shading language instead of GLXL. We have all the shaders. We have all the transforms and the mesh data. But then we even get to think about how do you tell the GPU to actually run those commands. We have to take the actual draw commands and encode them into these command buffers that we send down a render pipeline to the GPU. So Metal actually increases the complexity in return for giving you more performance. Now, this summer, Apple introduced a few new things. MetalKit, which sort of sits on top of Metal and makes it a little easier to manage a lot of those details. There's Model.io, which helps you read in meshes and do fun stuff with them. Does some neat rendering effects. And then there's also a sort of SpriteKit over on the side. I mentioned SpriteKit because you can actually mix SceneKit and SpriteKit together, and you can get 3D effects in your SpriteKit games. And you can also take SpriteKit and bring it into your SceneKit program. So there's some neat little things out there as well that it's working together as an ecosystem now, not just a couple separate SDKs. In general, these are your trade-offs. SceneKit, you get the rapid development, you get the scene graph. Metal, you have all the low-level stuff. OpenGL, now one of the big things that sort of came out this summer, when Metal was introduced a year ago, it wasn't really apparent what was the future for OpenGL on Apple platforms. And it's really become clear with how they brought Metal to OS 10 and just some of the things that engineers said maybe while talking to them, that OpenGL is not really an API they're looking to improve in the future at Apple. So if you're banking on OpenGL, it's probably time to start taking a look at Metal for Apple platforms. It's still supported, and it still supports OpenGL ES3, which is pretty good. OpenGL itself is, realizes that their customers are looking for different ways to do things and have hit performance bottlenecks. And that's why, companies, not just Apple, but AMD has a thing called Mantle, which is very similar to Metal, and NVIDIA has one, and Intel has one. They're all very similar, and OpenGL is working on new efforts to do the same sort of thing. But that's not out yet, and so that's something we have. But we're focused on that. But OpenGL is still pretty useful for compatibility. If you want to do graphics and you want it to run on Android, maybe using the native SDK or something like that, then you can do that with OpenGL still. Or maybe you have OpenGL code already from a desktop application or something and you want to port it, in which case you might not want to switch gears yet. So let's jump into SceneKit. It's got all sorts of cool stuff. As I mentioned, you're working with objects and transforms. You get to have vectors and things like that. You don't have to get down to the nitty-gritty of typing in vertex coordinates and stuff like that. It's got a physics engine built in, all sorts of nifty effects. It's not super performant, but it's not bad either. It's the sort of thing you always have to test. But it's so easy to use that it's a great place to start out. So what does it look like when you're programming with a scene graph? Now, first off, you can generate scene graphs programmatically. You can also create them in a 3D modeling tool. Blender's a free open source one. There's all sorts of premium good ones as well. And you can export your models in DAE format, which is a collada format. And then SceneKit knows how to read those and manipulate those. Or you can create your scene graphs programmatically. Or you can mix and match too. Here's a simple scene graph to make what will become a tree. And you have sort of a root node, which is just a group. A scene graph is just a tree. In SceneKit's case, the geometries are sort of hung off the nodes of the tree. So you can actually share geometry between nodes. Here's sharing geometry between nodes. The actual spheres and columns that compose this sort of tree model would actually be shared between all these nodes. So you wouldn't have to repeat your vertices in memory several times. And here's some Objective-C code that's easy to do in Swift as well, actually even easier to do in Swift, that kind of creates this model. And so it's pretty easy to use. You make a cylinder, you make a node that contains the cylinder geometry, and then you add it to your tree. So that's what SceneKit looks like, programming with SceneKit. If you were going to do something like create a bar graph, maybe you have you want to rate your sales over time or something like that. You could very easily see writing a for loop that would go through something and create a box of the right height for every element that you wanted to graph, and maybe even a 3D text label for underneath it. 3D text is very easy to do in SceneKit as well. So let's actually take a look. I don't like to go too long without showing a demo. But let's take a look at a SceneKit bar graph thing, I think. I think this is the bar graph. We'll see when we run it. Here we go. So here we've got bars that were set up with different heights. You can actually see the code behind the simulator. It's automatically doing lighting for us. It's done some 3D text generation. I don't know if you can see it from out there, but the text is a little funky looking. It's not the font, it's just how smooth the smoothness setting is kind of set down. That's something that apparently changed in Xcode 7. And we've also got this reflective floor. So in terms of the scene graph for this, we've got a group that has these 4 bars and the text, and then we've got a floor node, and we probably have a light node that's giving us the lighting, although there's default lighting as well, and maybe a camera node as well. So you can do all these things, put them all together, and it's pretty handy. Like I mentioned, let's see, I was working on bringing a scan of my head in, but I didn't quite finish that, so I'm sorry I won't get to show you that. But here's a little model that I actually built in Blender. So here's the Blender version of that model. I exported it as a collada file. brought it in here, and then I actually have this set as the default model for a SceneKit view in the storyboard, and it just loads up and automatically shows in the iOS app. So you could actually do this without any code. All you have to do is go into the storyboard file, and you see here, it's hard to read, but here's a SceneKit view. And I have the box and torus model set as the default. And so you set that up. You can even change it. Yeah. Well, let's go ahead and try this. I don't know if this will work or not. I haven't tried it. I don't think it'll look right because I think the normals are wrong for my head. But there we go. Actually, oh wow, hey. So that's me. It looks a little dark because the normals are inverted. The normals are pointing inside when they should point outside. And so that's something I had to go change in the mesh. That's something you tell your artist. Your artist would give you something like this, and you'd go in and say, oh, it looks all dark. And you'd go change it and select everything. And he or she would just flip the normals around. I'm not an artist, so I don't really know how to do that. I'm much better at programming the scene graphs than I am at creating them in Blender. Anyway, so that's some cool stuff you can do with SceneKit. It's got a whole ton of other stuff as well. You can do, as I mentioned, it's got the physics engine, so it's got collision detection and stuff like that built in. It has particle systems, so you can do fire, smoke effects, water, things like that. Interaction, it's got the ability to do hit testing for points on the screen. So if you want to do interactive stuff, if I wanted to select a bar on that 3D graph, you can do that, and that's very helpful because that's a difficult thing to program. You don't have that at all in OpenGL or Metal. It's got filters. You can put core image filters on top of it, and that's pretty neat. I'll show you that in a second. And you can also use it in playgrounds. I haven't seen anyone do that lately, but that's kind of fun. You can also use it with SpriteKit, as I mentioned. So you can actually do things. You can do it in two different ways. You can have a 3D node that's done with SceneKit. You can have that be a node in your SpriteKit game. You can also take a SpriteKit game and actually put it on a SceneKit object, which is pretty cool. If we have time at the end, maybe I'll load up a demo of that for you. It's pretty wild. If you're anybody here doing the game jam tomorrow night? A few people. So if you use SpriteKit, just like at the end, take your game and put it on a spinning cube, and then you'll win. All right, performance-wise, SceneKit is not as optimal as what you might come up with in Metal. That's because it's meant to be very easy to use, and it doesn't know how your scene graph is arranged. Well, I guess it actually does, but it it can only make certain assumptions about it, and it doesn't go through a lot of the performance optimizations you would use. So this is a little old, but a while ago I did a demo where I had 10,000 cubes. No, yeah, 10,000 cubes on just on the screen, all kind of rotating a little bit, and I was getting about 10 frames per second on it. If you do the same thing on Metal, you'd easily get 60 frames a second if you were structuring your rendering loop correctly. And that's because it just doesn't know that these are all the same objects, so it doesn't know that it could get those advantages by say not resetting its render state every time or something like that. Now, again, it's a high-level SDK. So here's a little demo I'll show you in a second, where we just have a spinning spaceship with a particle system and then a core image filter on top. And it winds up being about 65 lines of Objective-C. But if you run it and you just put it in the OpenGL debugger, which is pretty cool to run if you haven't ever run it, you find out that it's got over 300 OpenGL calls that it's making. So, and that's just a call. That's not talking about the setup to make the call if you have to calculate things or something like that. So it's saving you a lot of work by just doing all this stuff for you and keeping it behind the scenes. Let me show you that demo real fast because it's pretty cool. These demos tend to run better, by the way, on the devices than they do in the simulator. So even this one looks a little choppy, but it actually runs quite well on the device. So here we've got the spinning spaceship, and then there's a particle system generating flame coming up back. It's also, you'll notice the colors are inverted. The dark is light and the light is dark, and it's pixelated. And we've done the inversion, the color inversion, and the pixelation using core image. Just created a couple of core image filters that could do that and put it right on top. So, you can get a lot of cool effects very easily with SceneKit. Okay. So that's SceneKit. Honestly, we could spend like the whole time talking about SceneKit or any of these, but the whole point of this is to kind of compare and contrast these different SDKs. So let's talk about OpenGL. Now, since the straw poll indicated many of you know OpenGL, we may go through this on the quicker side. But as you may know, with OpenGL, you're working certainly at a lower level in SceneKit. You're talking about meshes. You're telling OpenGL how the mesh is laid out in memory. You're setting up shaders, maybe writing some shaders in GLSL, and dealing with this C API that's, I don't want to say it's kind of clunky, but it's certainly, I don't know, unique. It has its own special flavor. Now, OpenGL is cross-platform, so the same OpenGL code that you write on iOS, it works on Mac, it can work on Android. There's always little differences with certain things. You can always find little bits, but in general, it works pretty well cross-platform. Now, here's some OpenGL code that will render a triangle. It's actually fairly simple, except for the boilerplate that compiles the shaders. So there's a lot of work you have to do to just set up stuff, and what I do and what most OpenGL programmers do is they have their toolkit that does this sort of stuff, and they just load it in every time and use this. You don't write your boilerplate code every single time you want to do this. So it's difficult to get one triangle up on the screen because of that boilerplate. Once you've got one triangle up on the screen, though, it's pretty trivial to get 2 or 2,000 or however many you need. So, there's a command to clear the screen. There's commands to describe to OpenGL how your mesh is laid out. And then GL draw arrays is the actual OpenGL call that goes and kicks off the whole rendering pipeline. Now, GL draw arrays will use your current vertex and fragment shaders to actually do the rendering. So that's where the OpenGL shading language comes in, GLSL. So it's a C-like language. It has special reserved words, GL_position, GL_fragment color, or frag color. And it also, by the way, has nice support for vectors and matrices, so you can do things like 4x4 transforms that you need to do with graphics very easily. Oops. So in general, the process is you set up your shaders, describe your geometry, set up your rendering state, if you need alpha blending or if you're doing some stencil buffering tests or something like that, you need to set up that state. You issue your draw calls and you repeat. Now, often with OpenGL, you hear people talking about the OpenGL state machine. So it's, I think, useful to remember OpenGL is a C API, and so it has kind of this global state that's associated with your OpenGL context. Your OpenGL context is just where you're drawing to. It's probably your window, maybe it's off screen if you're doing, multi-pass stuff, or you're just using OpenGL for efficient rendering. But that's where the OpenGL state is stored in your context. That has things like what shader program are you using right now? Is Z buffering turned on or off? Is alpha blending turned on or off? That sort of thing. So all that OpenGL state is stored there in the context. Your program sets up the state, and then you do the draw call. The state goes into the shader program, some parts of it, and the draw call will send in all the vertices to the shaders, and then that will go out and show up in the frame buffer after going through the shading process. So the shading process, we've got vertex and fragment shaders. That's what we usually think about with OpenGL. And by the way, this all applies to Metal too. Metal does all the same stuff. So we're talking about OpenGL, but this is kind of graphics architectures in general. Now, what Metal doesn't have is geometry and tessellation shaders. Metal does have compute shaders. But these are types of shaders in OpenGL used for other things. The geometry and tessellation can let you do things like level of detail. You can send in one triangle and get out a bunch of triangles to do curved surfaces or something like that. And the compute shaders are just for doing high performance computation on the GPU. And that's because the GPUs are so good at doing math. So if you want to hear about that, go to Jeff's talk on Wednesday. Not OpenGL, but actually Metal doing that. So I think it's instructive to go through just to walk through what these shaders do, so you kind of have a feel for how they fit in, how GLSL fits in with your Objective-C or Swift code. So you've described your geometry to OpenGL. We'll actually get to that in a minute. When you're ready to draw and you call draw arrays, the first thing that happens is that geometry gets projected onto the screen. And I like to use this little diagram I drew once of a little painter, painting something on a canvas. And if the painter is painting something out in the world, then it's kind of analogous to projecting that thing in the world onto their canvas. And actually, artists often will use something like a pane of glass, and they'll kind of stand at a specific point and then use that pane of glass to trace what they see through it. And it's the exact same process as what we do when we render onto a computer screen. What happens after the vertices get projected, OpenGL is going to figure out which pixels on the screen need to be filled in, which pixels need to be rasterized. And it's going to do that for each triangle. And then it runs the fragment shader to figure out what the color of the pixel is. So of these four things that happen, you first call OpenGL C API calls to set up the geometry. OpenGL, after you call draw arrays, will project all the vertices using your vertex shader. Then OpenGL will rasterize it. It does it on its own. You don't worry about that. It just happens. And then for every single pixel on the screen, it's going to run your fragment shader. So the reason it's architected this way is because it can do these two shader steps trivially parallelized. The vertex shaders and the fragment shaders, they don't actually know about the other vertices and the other fragments that are being projected or rendered when they go through. So you can just have 20 different little bits of your GPU go to town on all these vertices and project them or shade them running your GLSL code, and it happens very efficiently. So that's why it's designed this way. Now, before all that happens, you have to describe your geometry to OpenGL. And this is where we start to get into some of the concerns that we have with Metal. And that is, we have to explain to OpenGL how the vertex data is laid out in memory. We have to say, okay, we've got positions, we've got normals, maybe we have texture coordinates. How many bytes are we using for each one of those? How many bytes are we using for the whole thing? Where does each part start? We've got the coordinates at one part, the normals in another part. Are they interleaved or are they stacked up on each other? Do you have an array, 3 different arrays, or do you have one array with 3 different things in it? You have to explain all that to OpenGL somehow. And we won't go into the details, but you use code that looks like this to explain to OpenGL what your data looks like. In Metal, you're going to have to do the same thing. And Metal has data structures to fill all this in that you set up with their buffers, their geometry buffers. But if you compare that to, say, what we were doing with SceneKit, that code I just showed you, this is a cube, and describing a cube to OpenGL. In SceneKit, we say SCN box, and we give it a size And we can even have it round the corners for us because SceneKit's like that. And then you just create a node. So that's where we get some of these big wins with SceneKit is just not having to write all that stuff. Now, ideally, you'd put that stuff in a library, so you could just say, hey, give me an OpenGL cube, and you can do that. But even then, there's still abstractions. Like you have to get pointers and stuff like that. If you're going to be doing OpenGL, then there's the GLKit library to make things a little easier for you. You actually, with GLKit, you don't have to write your own shaders. It's got built-in rendering for you. And it also has matrix manipulation routines, so you can do matrix math, and they're actually accelerated. They use the SIMD routines to do things very quickly on Neon processors. And it takes care of loading textures. I haven't talked about textures yet, but anytime you want to use an image in any of these things, it always adds another little bit of complexity. With SceneKit, it's pretty easy. With SceneKit, you can say, hey, set the contents of my material to be this image. And it's kind of cool because it takes advantage of Objective-C dynamic typing to just look at whatever you're setting it to. And it's like, oh, is that a color? OK, I'll make it this color. Oh, is that an image? OK, I'll make it this image. But GLKit can make that a lot easier for OpenGL. And MetalKit in Metal does something similar. And then there's the GLM math library. That's a C++ math library. It's not from Apple. It's somewhere else. But it gives you GLSL-like math routines that you can use for all these things, for creating matrices and manipulating them and all that. So you don't have to go write your own math routines. OK. Before we jump down to Metal, let's talk a little bit about Model I/O. Model I/O I've just started messing with, and we won't go into detail on it because of time constraints, but it's a pretty neat library. So one of the big things that was missing from GLKit is the ability to load meshes, to get this 3D model that your artist has given you and then load it into memory in OpenGL. And nobody wants to write their own Collada parser. Even the people who wrote Collada parsers didn't want to write Collada parsers. They wanted to work on the game engine, but that's what they got stuck with. So Model I/O is really handy. It can read in your meshes. It can actually export meshes as well. That's super useful. But then it does a bunch of other really cool stuff. And I'm going to just have to refer you to the WWDC video. Who saw it on Model I? Okay, one got great. Darn, I should have loaded up those demos. But it does a couple other really cool things. One is light maps. So if you have like a room like this, we have all these lights on the ceiling, and if you look at the walls, they're bright on the bottom and dark at the top. And the way we would do that in a graphics program is we would probably take this geometry of this room and look at the intensity of the lights and the shapes of the lights and figure out what color everything should be as we walk around. Because as I walk around the room with these diffuse walls, the color doesn't change whether I'm over here or over here. It's going to be lit up in this kind of arc pattern. And so you can do that with what's called a light map. These light maps take a while to compute, but once you do all this computation on them, you can render everything very quickly because that lighting doesn't change. Now, lighting like this projector might change as I walk in and out of the beam. My arm gets light, my arm gets dark. So that's something you'd want to do dynamically. But the light map can let you do this diffuse lighting very quickly. So it has routines to calculate these light maps, as well as something called ambient occlusion, which is I'm not going to try to explain the effect, but it's a very noticeable effect that you'll see. And what it means is that if something is in, I said I wouldn't explain it, but yet I am. If something is, say, down at the bottom here, it's going to be darker than if it's out on the table here. Not so much because of shadows cast by the lights, but sort of it is because of shadows cast by the lights, but it's sort of a hacky way to do it. So it gives you this nice gradient up to the base of an object that's, say, sitting on another object. and it gets away from this, this fake effect you often see where like there's an object resting on a table, but you can't really tell if that object is up close or backwards or something because the shadows aren't calculated right for the table. Like the shadow for the table is calculated by looking at the lights, but it doesn't really take the object into account. So ambient occlusion helps with that. If you look it up on Wikipedia or something like that, you'll see some very good examples, and you'll be like, oh yeah, I see that all the time. The last cool thing it does is voxelization. And this is a side effect of actually doing the light map calculation, is that it has routines to take any arbitrary mesh and turn it into a 3D grid, turn it into a volume of voxels. And there's a very cool demo that they did in the WWDC session where they just took a 3D model of a raccoon or a fox or something, and they turned it into, ran the voxelization on it, and then at each voxel that there was a part of the mesh, they put a ball, and then they turned on the physics engine and let all the balls fall and bounce off each other. So it's kind of worth checking that out. Anyway, Model I/O, it's meant to work with Metal. It can also work with OpenGL, and I believe some bits of SceneKit, although SceneKit has some of that stuff built in. But it's very handy for reading in your model assets. So be sure to don't write your own 3D data format parser, use Model I/O instead. Okay, so let's talk about Metal. And no talk about Metal is complete without the picture of Federici throwing the horns. So we have to show that. It cracks me up every time he talks about it because he does that. So why do you want to use Metal? Why was Metal introduced in the first place? What was wrong with OpenGL? OpenGL was starting to hit this performance bottleneck where if they wanted to, if you wanted to get to the next level of performance, you needed much finer grained control over what was happening on the GPU. Because the GPU with OpenGL is effectively single-threaded. You can send in your draw commands, and then you basically have to wait until they're done. And if you don't wait, then well, you're waiting. Like if you have to wait, you don't have a choice. Now, the GPUs can have multiple processors, and there were things you could do with multiple OpenGL contexts and stuff like that. But it became very difficult to do something like, calculate all your collisions while you were waiting for the rendering to finish. And so Metal was introduced to give you much finer grained control over the scheduling of the GPU and where these things happen. And the result is that you can draw many more things on the screen than you could with OpenGL with the same amount of time. They did a bunch of other stuff, like you could compile your shaders in advance. They actually did a very nice memory model so that you can have computation shaders that work in concert with rendering shaders, which is really cool. They cleaned up a lot of the ways to get in and out for computation shaders, so it works a lot better than OpenCL did. But this is some of their reasoning behind Metal. The downside of all of this is not only do you have these vertex and fragment shaders that you had to set up with OpenGL, now you have to start worrying about all sorts of other things, like what device are you running on? You have to set up a render pipeline that handles all your rendering commands. You have to set up a command buffer to hold those rendering commands. You have to write your shaders. Then you have your mesh and texture resources, so you still have to put your meshes in memory, and you still have to describe those to Metal. And finally, you have to synchronize it all. You actually get to use semaphores with your rendering code. So it adds a lot of complexity to the rendering process. And if you go and look at the Metal programming guide, you'll find this is the code required to just draw a triangle. And so this I pulled straight out of the Metal programming guide. It's actually, though, I'm purposely scaring you a bit, but it's not actually as bad as it seems, because a lot of this is actually boilerplate stuff that you wouldn't do every frame. And we have boilerplate in OpenGL too, so that has to exist. Really, for Metal, this is the part that matters, is you have to deal with your render pipeline, you have to set that up properly, and I think there's probably a command or two up here to put in as well, but you have to, once your render pipeline is set up, you draw your primitives with your pipeline, and then you say, okay, I'm done with that command, and it goes down the pipeline and executes, and you can execute more commands. You could stack these up, by the way. So that's one of the things. If this were an OpenGL command, the GPU would kind of block. It wouldn't block the CPU, but the GPU might block your frame, and here you have much better fine-grained control over what the GPU is doing. So since there's all that boilerplate, it's still kind of a pain, and that's why they introduced MetalKit. And MetalKit was introduced this summer, and that makes it a lot easier to get going with Metal. What it does is it handles the setup of the device, which is, believe it or not, I mean, it doesn't sound like a big deal, but if you start looking at the Metal documentation, you see that it's a real pain. Like, these devices objects are kind of confusing. But it makes it easy to set it up. It sets up a view for you, and so you have your view, and you can actually just subclass the MTK view class. Oh, and by the way, it's implemented for Mac and iOS, so it's a subclass of UI view and NS view, which is kind of neat. And it can handle texture loading for you as well. So if you're going to actually write a serious Metal app that's doing rendering, what you're probably going to do is you're going to have Metal, and you're going to be writing your shaders in Metal. You're going to have MetalKit on top to just help you out if you're, if you're writing, if you work for Epic and writing Unreal Engine or something like that. Like, maybe you'll dispense with MetalKit, but most of us are going to use it. You'll use Model.io to read in your mesh assets, and then your app is going to sit on top of all three of those things. So that's kind of your plan for doing a Metal app if you're going to do it, in the near term. Let's take a look at the Metal shading language. It's built off of C++ 11. I don't hear any cheering. So it's kind of funny because this came out at the same time as Swift, and so it's like two completely different directions, which is presumably a left hand doesn't know what the right hand is doing, sort of thing. But so you have some things like these double bracket things which are used to sort of explain how the attributes are in memory. So remember I showed that graph of the memory with all the vertices and stuff. You have to do the same thing in Metal. Now, one of the neat things about Metal, though, is you send in like your positions and your text coordinates and your transform matrix all at once, and you also send in vertex ID, the vertex to transform. This is in a vertex shader. So Metal, you can actually look at the different vertices and use them. It's not isolated like OpenGL. In OpenGL, if you're transforming vertex 0, you don't know what happens happening to vertex 1, or even what the data is for it. Same thing with 1 doesn't know about vertex 0. With Metal, you can actually break that constraint, and you can figure out. You can say, hey, okay, I'm rendering vertex 2. I'm actually going to blend it from vertex 0 to vertex 3 with some sort of weighting or something like that. So you can do some cool stuff there. So this is just what Metal looks like. Now, Metal did do a pretty good job of actually making it easy to load up the shaders and stuff like that. It's a lot more streamlined than OpenGL. And you can say new function with name, and you give it the name of the function in here, and it returns the right handle for that to send out to encode in your rendering commands. Okay, we haven't seen the demo. Now, I can't run Metal on my laptop because I haven't upgraded to the Captain yet. But not this one. But you can see it running here. And it's, yeah. And so that is the, this is the sort of many cubes. This is like 10,000 cubes as well. And it goes nice and fast. It's actually not the most efficiently implemented thing. It takes, it actually has 10,000 transform matrices in there, which is, probably more than it needs, but it's kind of nifty. So be happy to show that to you. So which one should you use? Let's kind of sum up. I think definitely in this day and age, and a year ago, I think the question was a little harder, but now SceneKit, it's matured a little bit. It's got a ton of stuff in it, and I would usually start with SceneKit, especially if you want to do something like make something like the bar graph or some little splash of 3D. That's the phrase I thought of in your app. If you want to have some cool little 3D effect on the screen or something like that. I work for a bank during the day, so maybe we have a flippy golden coin or something. Redeem your credit card rewards. Something like that is really easy to do with SceneKit. And it works very well with UIKit as well, so that's another good reason to do it. Simple visualizations, creativity apps, something near and dear to my heart. Especially those work great with SceneKit because you've got that whole graph structure. You can just start modifying it willy-nilly, and you don't have to worry too much about resource management or anything like that. Plus all of the interaction that you get with hit testing and stuff like that. That's pretty neat. Simple games as well. You do start to hit performance limits, but there's a lot of great stuff you can do just straight out of the box. Plus, I haven't even touched on like the built-in level editors and stuff like that in Xcode. There's all sorts of great stuff there. Metal is great. Of course, if you're writing a game engine, you want to get into Metal. But more interestingly, if you're doing GPU computation, maybe doing audio processing, something like that, high-performance graphics, of course, that's where Metal comes from. OpenGL, if you have like a legacy app, something that you're bringing to iOS from an old code base, maybe you want to look at OpenGL, or maybe OpenGL is the easy path. Android compatibility. But in general, in this day and age, if I were starting a new project, I wouldn't want to start with OpenGL if it were a brand new, fresh thing. I would only do it if I had some tie to the past that I needed to use it for. So that's sort of where I am. And I used to teach OpenGL, by the way, so that's it's kind of sad. I put together just a few good resources for you. So SceneKit, there's a book out by David Rohnquist. I don't know if I pronounced that right, but SceneKit book. It's a really neat book. It's an iBook, and it's got lots of interactive graphics. It's pretty darn cool. So I definitely recommend getting that. This guy Warren Moore. Is that? I don't know if that's his actual Twitter handle or not, but Warren Moore, that's his name. You can find him if you search. He's writing a book called Metal by Example, and he's been working on that for some time, and he's got a bunch of chapters up on his blog already that you can take a look at. So that's pretty cool. It covers rendering. Also goes into a lot of the just general rendering theory, a lot of the 4x4 transforms, why we use them, that sort of thing, which is handy. Metal computation, Jeff's going to talk about that Wednesday morning, so if you're interested in GPU computation, attend his talk. OpenGL, if you do want to learn it, and it's still pretty handy, there's a great book by Eric Buck on OpenGL. It covers programmable pipeline OpenGL, which is to say the OpenGL with the shaders and stuff like that. So that's what I had to talk about. Thanks very much. Apparently we're at 0 time, so all right, thank you.
Real quick, do you have the examples that you ran tonight?
Yes, and I'll put those up on Dropbox and put a link in. What do people prefer? Do people prefer Slack or the Twitter or?
Slack's great.
Slack's great. Okay, I'll put it up on the Slack. Next. Okay, thank you.